So we've been talking about Coulomb's force and electric fields, and we know how they're related. Coulomb's force is equal to the test charge times the electric field of the source charges. Okay. Now I want to consider the case of a charged particle. So this is my QT. We'll just make it positive for simplicity inside a capacitor. Okay, so I know that the capacitor electric field points from positive to negative, which means the force on a charged particle would also be in that direction. Okay, so our source charges would be this capacitor. Now, we could analyze this, and we've already done it quite a bit with kinematics. You know, I could say how fast if I release this particle from rest, how fast will it be going when it hits the negative plate. I could use Newton's second law and dynamics, or in kinematics, to figure that out. But just like we saw in a mechanics class, is that you can also analyze mechanical systems using energy, and often it's much easier to consider that because you don't need to worry about the directions, the vector nature of things. That we can try and recast this in terms of energy. So let's remember how that works. First of all, work is defined as force times a distance. So I'm going to use an S coordinate here, and I'm going to define S to be pointing this way with 0 at the negative plate. Okay. Now, to be careful, I really need to have the component of the force in the direction of S. So to find that, what we do is we use the dot product between the two vectors. Now remember, all that's doing is finding the amount of force in the direction of S. So I could just write Fs times ds. That's all that dot product is doing. But to formalize it completely, then I could say, well, if the force is changing, I need to integrate from some initial position to some final position. Okay? So that's the full formal way to do it. But I want you to focus on the conceptual, is we know work is positive if the force is in the direction of the motion. Okay, so if the force is pushing in the direction of the motion, then it's positive. And it's negative if the force pushes, but the object moves the opposite direction. Okay, so if I push on a refrigerator up a ramp, and the refrigerator moves up the ramp, then that is a positive work I'm doing on the refrigerator. But if I'm pushing the refrigerator up the ramp, but the refrigerator is sliding down the ramp, then I'm doing negative work on the refrigerator, or the refrigerator is doing positive work on me. Okay, so that's the main idea. So reviewing that. All right? And so in this case, what is the work done on the particle by the capacitor? Okay? Well, we can write that the force on it is Q test times the electric field of the capacitor, okay, dotted with ds. All right, and the capacitor, the electric field capacitor, is pointing to the left, but S points to the right. So these are opposites, so they give us a minus sign. So negative. I'm going to go ahead and pull out the QT since it's constant. Okay. So I've taken care of the dot product by noting that they are opposite each other, which would give me a minus sign. Okay, and then I note that, well, E capacitor is a constant. The electric field of capacitor is constant. I can pull that out. All right, and I'm just left with an integral from an initial position to a final position of ds, which is just a displacement. So that becomes negative qt E capacitor S final minus S initial. All right, and that equals the work. Now, the capacitor is doing work on the particle. The force is to the left, and the particle moves to the left, which means the work should be positive. But I see a minus sign right here. Well, being careful, because of this coordinate system, we chose to the right being positive. That means when the particle starts over here at S initial and ends over here at S final is closer to 0 than S initial is. So this is a small number minus a big number, and we get a negative sign. Okay, so that still ends up working out. And I can just separate these two out and add that across, or switch their positions. And I could say QT E capacitor S initial, so minus a minus a positive, minus QT E capacitor S final. Okay. Now, what's interesting about this is that we have the change in position, but our S final in this case, we chose this as a reference of 0. So that makes this one 0. All right, and we get QT E capacitor SI is equal to the work done. And that really is just the change in position. So with this being just the change in position, I can kind of get rid of that initial since I'm using 0 as my my change. And so this is the work done on the particle. Okay. Now I can apply that to the work kinetic energy theorem for a particle, because this should then be equal to the change in kinetic energy. Work equals change in kinetic energy for a particle. And so that's how much it should speed up. And so even if it wasn't starting from rest, that I can tell that that's how much it would speed up. But I also know that that's the same thing as the negative change in the potential energy of a system. So this allows us to define potential energy of a particle inside a capacitor. Okay, and so writing that out, that's negative U final minus U initial. Okay, or it equals U initial minus U final. Okay, and so what we can do with all potential energies, we need to establish some reference point. And so in establishing the 0 position to be our negative plate, we also call that our U0 and often call it to be 0, but this is our initial position, and then this would be minus U0. Okay, that's our reference point. Whatever the value is here, this is going to be our value at wherever we started. Okay, and so we can now just connect the potential energy to this value right here and write that our potential energy of wherever we're at, we call it U electric, so that's the U initial, wherever we started, okay, is going to be equal to, if we add this to the other side, whatever our reference potential energy is, plus the difference there, plus Q of our test particle, E of a capacitor, and then the position wherever we are at, whatever location we're at. Okay, and so this is now our relationship of the potential energy inside capacitor, but I also want to emphasize that it's also related to our change in kinetic energy. So that's the potential energy of a particle inside a capacitor. It's an electric potential energy. When I place a particle here, it's not moving, but it's gonna, because there's a potential energy in the system.